So let's say we have a cup of water. Let me draw the cup. So that's one side of the cup. That's the bottom of the cup. That's the other side of the cup. And it's water. Well, let me say it's some liquid. It doesn't have to be water. Some arbitrary liquid. It could be water. So that's the surface of it. So we've already learned that the pressure at any point within this liquid is it's dependent on how deep we go into the liquid. And one point I want to make before we move on, and I touched on this a little bit before, is that the pressure at some point, it isn't just acting downwards, or it isn't just acting in one direction. It's acting in all directions on that point. So although how far we go down determines how much pressure there is, the pressure is actually acting in all directions, including up. And the reason why that makes sense is because I'm assuming that this is a static system, or that the fluids in this liquid are stationary, or even we could imagine an object down here, and it's stationary. And the fact that it's stationary tells us that the pressure in every direction must be equal. Especially, let's think about a molecule of water. A molecule of water, let's say it's roughly a sphere. If I have a molecule of water, let me do it in this corner because I'm going to need the space later. If the pressure were different in one direction, or let's say if the pressure down were greater than the pressure up, then the object would start accelerating downwards, right? Because its surface area pointing upwards is the same as the surface area pointing downwards. So the force upwards would be more, and it would start accelerating downwards. So even though the pressure is a function of how far down we go, at that point, the pressure is acting in every direction. So let's remember that, and now let's keep that in mind to learn a little bit about Archimedes' principle. So let's say I submerge a cube into this liquid, and let's say this cube, and let me draw the cube up here, so let's say this cube has dimensions d. So every side is d. d, d, d. It's dimensions d. So what I want to do is I want to figure out if there's any force, or what is the net force acting on this cube due to the water. Well, let's think about what the pressure on this cube is at different points. Well, at the depths along the side of the cube, we know that the pressures are equal, right? Because we know at this depth, say right here, the pressure is going to be the same as at that depth, and they're going to offset each other. So these are going to be the same. But one thing we do know, just based on the fact that pressure is a function of depth, is that at this point, the pressure is going to be higher, I don't know how much higher, than at this point, right? Because this point is deeper into the water. So let's call this P1. That's the pressure on, let's call that pressure on top, PT. And let's call this point down here, let's call that PD. Pressure on the bottom, PB. Right? And what's going to be the net force on this object, on this cube? Well, it's going to be the net force, let's call it F sub n, is going to be equal to the force acting upwards on this object. And what's the force acting upwards on the object? It's going to be this pressure at the bottom of the object, times the surface area at the bottom of the object. Well, what's the surface area of the bottom of the object? Well, that's just d squared, right? Any surface of a cube is d squared, so the bottom is going to be d squared. And then minus, and I'm doing this because I actually we know that the pressure down here is higher than the pressure here, so this is going to be the larger quantity, and that the net force is actually going to be upwards. So that's why I can, do the minus confidently up here. Minus the pressure at the top. So what's the force at the top? The force at the top is going to be the pressure on the top times the surface area of the top of the cube, right? Times d squared. And we can even separate out the d squared already at that point. So the net force is equal to the pressure of the bottom minus the pressure of the top, or the difference in pressure, times the surface area of either the top or the bottom, or really any of the sides of the cube. Now let's see if we can figure what these are. Let's say the cube is submerged h units, or h meters, into the water. H. So what's the pressure at the top? Well, so the pressure at the top is going to be equal to the density of the liquid, which I keep saying water, but it could be any liquid. The density of the liquid times how far down we are. So we're h units down, maybe h meters, times gravity. And what's the pressure at the bottom? Well, the pressure at the bottom, similarly, would be the density of the liquid times the depth. So what's the depth? It would be this h, and then we're another d down, right? So h plus d, that's our total depth, times gravity. All right, so let's just substitute both of those back into our net force. Let me switch colors to keep from getting monotonous. So I get the net force is equal to the pressure at the bottom, which is this. And let's just multiply it out. So we get P times H times G, P H G, plus D times P times G, D P G. I just distributed this out, multiplied this out. That's the pressure at the bottom. And then minus the pressure at the top, minus P H G. And then we learned it's all of that times d squared. Right? So immediately we see something cancels out. PHG, PHG, subtract, cancels out. So we're just left with what's the net force? The net force is equal to dpg times d squared, or that equals d cubed times the density of the liquid times gravity. Well, let me ask you a question. What is d cubed? D cubed is the volume of this cube, right? And what else is it? Well, it's also the volume of the water displaced, right? If I stick this cube into the water, and the cube isn't shrinking or anything, that I mean, you can even imagine it being empty. It doesn't have to be empty, but that amount of water has to be moved out of the way in order for that cube to go in, right? So this is the volume of the water displaced. Volume. It's also the volume of the cube. Volume of water displaced. This is what? This is the density. I keep saying water, but let's just say it's water, but it could be any liquid. This is the density of the liquid. This is the gravity. So what is this? Volume times density is the mass of the liquid displaced, right? So the net force is also equal to the mass of liquid displaced. So let's just say mass times gravity. Or we could say that the net force acting on this object is, what's the mass of the liquid displaced times gravity? Well, that's just the weight of liquid displaced. So that's a pretty interesting thing. So if I submerge anything, the net force acting upwards on it, or the amount that I'm lighter by, is equal to the weight of the water being displaced. And that's actually called Archimedes' principle. And that net upward force, due to the fact that there's more pressure on the bottom than there is on the top, that's called the buoyant force. And that's what makes things float. So I'll leave you there with right now, just to ponder that. And we'll use this concept in the next couple of videos to actually solve some problems. I'll see you soon.